Hi, this is Ting 3 from COMP 19024, Cluster and Cloud Computing. In this video, I would like to introduce the Twitter Analytics System. This project focuses on exploring the deadly sign of gluttony on social media. We collect the data related to fast food or junk food across the city of Australia on Twitter. Then we compare our results with official data from Orin. Firstly, we will introduce our system architecture.
I'm going to talk about our system architecture and our system design. To gather and then to analyze Twitter from social media requires a large amount of computing power resource. In this project, we are given 8 virtual cores, 36 GB RAM, and 250 GB of disk storage in total. In general, we divide them into 4 virtual machines. Each is dedicated for a part of work: a CouchDB, a real-time Twitter scholar, a OTweets scholar, and a web server. I'm going to talk each one by one. Our database takes an entire virtual machine. The reason is that we want to make sure the database server is robust and does not become our bottleneck. Considering that it might have a high traffic communication and some heavy calculation on CouchDB MapReduce. The CouchDB is running in a Docker container. The port in the container was being mapped to the local host, and the container volume was also mounted to the external volume in Nectar. This will make sure that other virtual machines can be successfully accessing database. And if we need to stop the Docker immigrating the data to another instance, external volume and its snapshot can ensure our data will not be disappear. Our second instance is used for a real-time Twitter scholar. As an unpaid individual developer, there are a lot of limitations on Twitter API's usage. Since our Orin benchmarks are based on past data, if we are going to compare with it, it is better to gather tweets also from the time that the Orin record was. However, such old Twitter API have a strict limit on the number of available tweets gathering. It only allows about 2,000 old tweets requests each month, which is even not close to what we need. So we decided to crawl real-time tweets from Filter Real-Time Tweets API and try to find old tweets from Unimail Cloud resource. This instance is dedicated for real-time tweets scholar. The scholar tweets will directly transfer to our CouchDB on the first instance by CouchDB HTTP APIs. Since the latency is not important in such operation, so it shouldn't cause any problem by using network transmission. The third instance is used to crawl old tweets. As I mentioned, we were trying to gather old tweets from Unimail resource. Those tweets are stored in CouchDB as well. It provides some views, which used Twitter post location and tweets post time as the keys. So we could directly gather these tweets by CouchDB APIs. However, most tweets from this resource actually don't have a place attribute, thus we must have a per filter to filter out those tweets that has a place attribute. Considering the amount of posts on this resource is around 19 million, we arrange one instance for this works. The last instance is a web server, which illuminates our results in virtual. This web server connects with the database directly and asks a reduce request every 5 seconds to refresh its result. So the results shown on the website can be up to date and synchronously changed with the database. This part is implemented in JavaScript and uses some technology such as Node.js and Express to deploy the server.
Next, we will show a demonstration for dynamic implementation.
Now our task is to build 3 servers. One is the DB server, and one is a web server. This is a front end, and another is a crawler. So let's run it. First is to copy the API password, which I have down here, and it's command V. It's sudo password. And it's now create all the security groups, and also the instance is being created. And it's all the informations and image IDs. Our basic idea is to from the information we get, and then we register one variable called IP effects, and then from that IP effects we can build 3 dynamic hosts in memory, so that we can get the IP address every time we create instance. And then based on the IP address we grab, like let's see the dynamic host, then we can operate on each host like DB server and crawler server, and then finally the web server. And you can see the first DB server is done, and we can see from the dashboard after it's refreshing. Yep, and crawler server is building up, and DB server is up. Crawler server is built up, and you can see from here. And now all 3 servers have been set up. It's the DB server, and crawler server, and web server, and all from here we can see, yeah, it's all done. And now we have to wait for like 90 seconds because there are things going on, and we don't know whether the dashboard or Nectar actually build up the server and open the port 22. So there may be some cases that the dashboard have shown you that you have built up the servers, but actually there is something still going around at the end, at the back. Here is, yes, at the new server. Yeah, you can see now it's entering the DB server, and the first task in DB server is environment setup. It's written here, like download some PHP stuff and change the proxy settings and install stuff. And now it's the volume from our where our database store the data. You can see this one, the tweets 100 gigabits. It's on the DB server now. And now it's running the Docker configuration, and we want to use a CouchDB image. And now it's second is crawler server. And then we enter yes. And then you'll see this one is for the crawler server. We have the environment setup task, and it's same to the first one. It's environment setup. Now it's cloning our GitHub repo, like the crawler code, and now it's actually running the crawler. And this is a third database, third server we wanna set up. It's our web server, and it's about front end stuff. And same from above. It's environment setup again, and also you need Git setup. Now it's running the front end, and we can see and this is our final front end page, and this is a crawler is still working. Every time refresh the web page, the crawler is still working, so which means our um, program is set up and the database is connected to the program, and also front end can connect to the database.
Then let's look at our front end. The website builds on the virtual machine instance. We collected 270,000 real-time tweets by using the Twitter API. Also harvested the historical tweets from Unimelb Research Cloud. The data has been analyzed at two levels, real-time and historical. From the real-time tweets, we analyzed the distribution of tweets related to junk food or fast food in different states and cities. We filtered the data corresponding with the coordinates in different states. Then present the percentage and display intensity by shade of color. It's easy to find that the northern territory accounts for 2.78%, which is the highest proportion, followed by the Victoria. In the second figure, it shows the fair trade rate in different cities. Melbourne City accounts for 2.699%, the highest proportion in 7 cities. We can also find that the ranking results of states is corresponding to the cities. By computing the percentage of these tweets over the total amount, we also find the distribution among metropolitan and remote areas. In this figure, we can find that it's obvious that most tweets are from metropolitan areas in most states. Especially in Melbourne City and Sydney, the tweets count is nearly 3 times greater than the remote areas.
After we analyzed in real-time tweets, we found that the big city in one state will send much larger number of tweets than the remote areas. So we collected historical metropolitan fat tweets for analysis. The orange datasets we collected stores the obese data from 2014 to 2015. Therefore, we harvested the tweets during this period of big city and calculated their obese rate. We compared the tweet rate with orange rate under same period and location. As we can see, the real rate is bigger than that of Twitter. This is because not all the gluttony people will pay more attention to intaking instead of sending the tweets when they are eating or drinking. But if we divert our attention to Melbourne, we will notice that the orange data of Melbourne is the lowest, but the tweet data of Melbourne is the highest. The lowest reason is that the awareness of overweight in Melbourne improved steadily during these years, which can be verified in next figure. As for the highest data, this is because Melbourne has a far greater number of fast food restaurants than other areas because of huge demand and the business environment. The obvious tweets we collected may be the advertisements sent by these restaurants, which means Melbourne has more noisy tweets than other areas. Another figure of historical analysis is the trend of fat tweets in Melbourne from 2014 to 2018. As we mentioned in last part, we found that the awareness of overweight in Melbourne improved steadily during these years. We can verify this phenomenon in this figure. Except 2016, which is an outlier of this graph, the fat tweet rate decreased slowly. There are few fat people during these years. We can deduce that people paid more attention to health during this period. The outlier is caused by the tokens in our token list, which may be corresponding to the hot topic in 2016.